So learning by cheating. We talked a little bit about this before, but I wanted to go into more depth and talk about how some of these things work. So a bunch of these slides are from either Gokul or from Sanjaban Chaudhry. In fact, one of the slides I don't understand, so that one's going to be fun when we get to that one. Imitation learning turns out to be a good technique for a lot of cool stuff in robotics, lots of other problems too. I'm going to focus mostly on the robotics ones because they're the ones I know the best. We talked about the Dean Pomerleau stuff. Katerina Muehling there used imitation learning where you can see she's actually moving a robot arm, teaching it to play ping pong, which is pretty cool. Katerina was a faculty here, although that work was, I think, at Max Planck. There was some amazing work that we won't get time to talk about today because it's not learning by cheating, by Adam Coates and Peter Veal, where they used imitation learning to learn acrobatic helicopter flight from human expert demonstration.
It's upside down?
Yeah, it's upside down, and it's part of a very impressive set of maneuvers that people can do. They got one of the world's best RC helicopter pilots to teach them how to do trajectories. You can learn to steer big outdoor vehicles, and we'll talk a bunch about inverse reinforcement learning and how that works later. It's a kind of different technique. To remind you, we focused on this idea of on-policy imitation learning, right, as opposed to behavioral cloning. And one of the things we talked about as non-policy algorithm was this dagger idea, where, reminder, what the basic idea is you learn a policy just by observing expert demonstration, and then you execute that policy, and then you get corrections to that policy, and you build a new data set, you learn the policy again, and then you keep iterating this. You just keep aggregating more and more data together, or run your favorite no regret learner. That was the thing we're going to use. We're going to use that a bunch in this lecture too. First thing that is worth pointing out is in this algorithm that we described right here, your corrections are just the steering angles, right? So the data you get from the expert demonstrator is just what action to choose. Right? So you get input as camera image. The camera image is generated by your own roll-in distribution, executing the learner policy, and the outputs are actions of what to do. Well, what could we do if I got more information? So what if instead of getting the actions, I could give you the expert demonstrator's Q values? So imagine there's two different actions, and you think about both actions you could perform on a state. So think about the driving example. You can turn left, you could turn right. Let's say those are the only two things you could do, steer left, steer right. And what I'll give you is not just what the expert's favorite action was, but I'll tell you what the expert's Q value was for each action. So I'll tell you how much cumulative reward the expert's going to get if we were to switch over control to the expert at that point after choosing the action. Does that make sense as an additional piece of information you could get? How could you get an estimate of that? I guess that's the first question. If you wanted to get an estimate of that, how much you get an estimate?
If you have expert trajectories from those states already.
Yep. Or if you actually just hand over to the expert, right? So you execute your policy for a while, and then maybe you choose an action at random, let's say, so I can get an estimate of at least one of the Q values, and then I hand over to the expert and say, you drive, and then I look at the total reward achieved by the expert. That's one way I could do it, right? If somehow the expert had a Q function that you knew, a critic of sorts, then you could consult that critic as well. We'll see some examples of that. Okay, why would it be better if we had access to those Q values? Why could it be better? Yeah.
It might be that two actions are almost similarly good.
Yeah.
You can learn the nuances of.
Well, maybe even more important, let's say two actions are actually the same, right? Let's take the extreme version, right? Well, then you know it's not actually very important to make that distinction. In contrast, you might see places where the Q values are very different, right? So one action is, catastrophically bad, and the other is not particularly bad at all. But then you know, boy, I better focus on getting that action correct, and it's much less important to get ones where the Q values are the same, correct? Right. Does that make sense? Okay, so you can get a more refined notion of this. We talked about this kind of unavoidable epsilon error, right? So we just posit in these kind of problems that there's some error that you can't beat, right? And the epsilon error we talked about before was in 0-1 loss. So, are you getting the actions correct or not, basically, right? There's a more refined estimate, which is let's try to train our supervised learner to get the cost or the Q-weighted actions correct, okay? So you could think about that as, here's a car example, and there's multiple actions you could choose. Here, there's not a big difference. The cars here, there's not a big difference between these key values. Here, there's a really big difference in the key values if you drive off the track, okay? And so then what we would ask is something different. We would say, hey, I want you to find the policy. There's an argmax missing here, I think, or argmin, depending on whether these are costs or rewards. Let's find the policy that maximizes the average under your own distribution, under the learner's distribution, maximizes the average advantage achieved, right? Or minimizes the average disadvantage if these are costs. They look like costs here. Does that make sense? So basically you just weight the actions by their advantages, right? Or their disadvantages. So it's really bad to choose a high disadvantage thing. If the disadvantages are, say, 0, it doesn't matter which action you choose. Okay, and that, yeah.
So do you need to learn a critic for the expert? So these are historic?
You either need to learn a critic or you need to just roll out the expert, right? That's another thing you can do is you can just apply the expert and see what the total cost of the expert is. So you're doing one of those two things to get that Q estimate, right? It's pretty common. We'll see some examples of actually learning a critic for the expert, right? And then using that critic in the algorithm. Okay, good. That version of this kind of online learning approach is called aggravate. Good, so we said imitation learning great for robotics, but there's some issues here, right? And Steve and I were in fact talking about this before class. It's not so easy for humans to do this kind of correction, right? So someone asked, like, how did Stefan actually do this super tux kart racer problem, right? And I described what he did is, first he would drive, right? That collected the first set of data. And then what he would do is the learned policy would drive, and he would be controlling the joystick, right? But he wasn't actually affecting the vehicle at all, right? And so that's weird. That's kind of a weird user interface. What he actually did is something slightly more subtle. He would affect it some fraction of the time. And as long as that fraction of the time that he affects it goes to 0, you get the same kind of guarantee. So that way, while he was doing it, he was having some effect on the behavior too. Okay, so it can be pretty hard for humans to do this task. And so there's a whole bunch of literature on figuring out, kind of minimizing the number of corrections being asked for by humans. Like when the learner's unconfident, that'd be one version. When the human thinks this is really bad, they just intervene. That's another version of this kind of thing. So it can be hard. It can be hard to generate enough data, right? So you may need to have a human do a lot of these kind of things. It's really hard for humans, if it's a human expert, to provide a critic or a Q value, right? The only way I really know how for them to do that is either one, literally let them take over and look at the cumulative reward achieved by the human and use that as a Q value estimate, or explicitly learn a critic, right? But a human is unlikely to be able to tell you the Q value for this action is 1,000, right? They can tell you you should choose this action or not. They might be able to tell you kind of relative importance, but they're very unlikely to be able to give you a numerical value. Okay, so how are we going to solve this problem? Well, we're just going to make the computer the teacher. But the whole problem is we're trying to get a computer to do these tasks, right? So what do I mean by make the computer the teacher? Okay, so I'll give you the OG version of this. So Stefan got bored of trying to teach computers to play video games by himself. And so at the time, there was this Super Mario competition. Everybody familiar with the Super Mario game? Old classic video game. I'll show you a video. Okay, so this is, for those who have never seen Super Mario before, this is Super Mario, some variant of it. what Stefan did to build the expert here is he actually built a very simple planner. So he copied the internal state of the game. This is a game where you could actually copy its internal state. He considered a tree of actions coming out from that initial state. He then looked at the total points scored over this tree of actions. I forget how many time steps, like, I don't know, 5, something like that. 5 time steps in the future. Looked at the total reward achieved by Mario, like the number of points scored, and the forward progress. Made up his own cost function, which was something like how much forward progress did it make, and what was the score, and did you die, right? Built a planner, and it worked. Okay. Then he tried behavioral cloning on this, so just supervised learning on the Mario, and it didn't work on that planner I just described, right? And it didn't work at all. Input features. Input features for the learner is literally a little grid around Mario with binary features as to what fell into those grid squares. That was the kind of input features.
You do a CNN or?
No. This is pre-CNN. Well, no, nothing's pre-CNN. CNNs are like, I don't know, late 80s. Yeah. But pre-easy to train CNNs, let's put it that way. And did supervised learning, I think it was actually a linear SVM on those features, was actually what was going on there. Supervised learning basically doesn't work, and it fails in a kind of interesting way. It's not in the video, sadly, but like Mario will like walk up to one of these green things, fail to make the jump, and then just get stuck standing against the green thing, and nothing happens. Which we'll see this in a moment. We'll see this kind of latching behavior. But use the planner to train the dagger loop thing did work. So that's kind of interesting. It's a sort of proof of concept. Turned out now lots of people have taken some variant of this idea and gone crazy with it. So one of the early ones was and I'll show you more details of model predicted control in a minute. It's very similar to what I just described. So this is UAVs in a motion capture arena. Okay, so there's a arena, UAV, that is planning to fly around in that arena. There's some obstacles in those arenas. Those obstacles are in known positions in the motion capture arena. Everybody know what I mean by a motion capture system? Anybody not familiar with that phrase? Okay, so you have cameras. You have an arena, like a fixed space. You have cameras up in that fixed space. They're infrared cameras. You attach to the drone little retroreflectors.
28 by 28 pixels. But your brain has no trouble recognizing.
The joys of YouTube. This is off on some next video. You put little markers on the objects in the arena, just like you would put in, maybe you've seen movies made where they put markers on the people to extract data. Do the same thing, you put them on the UAV, you put them on the objects in the arena. Now, a computer can extract exactly where the UAV is in the world and velocities by time differentiating those things and where the objects are in the world. And now you can build a little planner that will plan the UAV around the environment. Okay, that makes sense? Good. And now we can try to use supervised learning or the Dagger kind of approach to try to learn something that only has, for instance, camera access to that move around the world. Okay, so let's look at, in fact, the video will do a better job of this than I can. But what we want to do, the goal here, is we want to learn a reactive policy for a RC car, a remote control car, that is high performance in sort of outdoor rough environments, that takes things like wheel speed and camera images, goes into a neural network, and actually controls this. Okay, and let me show you a video of that. This is work by Byron Boots group. I think there's any words in this video. This is what we want to achieve, right? Sensor data in, some kind of learner, action. Could do it for people. Turns out people have, again, a hard time doing this as well as a computer can. Okay, so you could apply RL to this, very hard in the real world, for sure. It may damage the robots. Maybe many broken RC cars in this process. Okay, you apply imitation learning, as we talked about, from a human. But we have to get that, we either have to get the human or some other expert. We're gonna get some other expert. We need the like 2x speed version of this. Right? This is some of the early work on using continents to learn to drive. Okay, we already talked about what imitation learning can be challenging. They rehashed that using Stefan's images. Cool. Okay. Rehashing the idea that we're going to use the learner's policy to avoid confounding errors. And then they want to drive faster than actual humans and not crash. And that's the robot they put together. It's an RC robot. Controls are steering and throttle. As you can tell, this is a slow-mo. So here, they are in fact using a continent on a sequence of images. Okay.
The last few frames.
Last few frames. Yep, literally last few frames. Okay, so what they built is an algorithmic expert. Maybe I'll pause it there. They built here is an algorithmic expert that cheats. So it cheats in the following way. It has a GPS system, so it's an outdoor robot, has a GPS system, has an IMU in it. From those two things, they can put together where the vehicle is on the track, how fast it's going, maybe accelerations it's feeling as well. So they take that sensor data, they put it through state estimation, meaning they try to figure out where the position is, what the velocities are, et cetera, by smoothing that data out. And then what they do is optimize for a plan. So they look out in the future, some number of seconds, come up with a plan for a very simple model of the vehicle, right? May not accurately capture slip, things like that. They execute the first step of the plan, get new information about where the vehicle is, again, create a plan out into the future. I don't know, think about it as 3 to 5 seconds, execute the first step, do it again and again. Does that make sense? This general idea of create a plan, execute the first step of the plan, and iterate it again is often called model predictive control. And see that again and again. It's actually not too hard to get this to work. You have to come up with some reasonable cost function to get it to work. You have to come up with some reasonable model of how the vehicle is going to move. But it's a reasonably easy thing in contrast with getting this giant neural network to be able to drive the vehicle.
So this is done while the car is driving? The optimization?
Yes, it is done while the car is driving.
It take a few seconds, you said?
No. The control optimization is almost certainly in the under 100 milliseconds category. The simplest version of this is really, really simple. So I described the simplest version of this. You have a library, you have what's called a trajectory library. So I'll give you the kind of the simplest version of this all. You have a trajectory library. Think about this as a sequence of commands that you could execute. So maybe your sequence of commands is you hold the steering wheel where it is and you step on the brake. Okay? That's one possible trajectory you could execute. And think about now simulating that forward for 35 seconds. Maybe another one is you make like an S maneuver. So you hold your foot on the gas and you make like a little bit of a left and a little bit of a right. Okay? Imagine building a whole library of these. You build, I don't know, maybe several thousand of these. Okay? And now you forward simulate them all. Again, it's a very simple simulation of the vehicle, right? So think of a very simple, almost kinematic model of the vehicle. And then you ask, which of these has the lowest total cost for the next 5 seconds, right? You pick the best one of those trajectories, you execute 100 milliseconds of what it wants to do, and then you do the whole thing again. Okay? That is the expert in a nutshell. Now, the expert has no idea what the camera images look like, right? Doesn't use them at all. It's not using any of that information. It's just using a model of the track where it's expensive to hit the wall of the track, and and the position of the vehicle on the track. Okay. Good. And now the whole game is, there's a low-level controller that actually moves the wheel, et cetera, moves the gas, et cetera. And there's a safety control system. But now what we're going to do is we're going to use this expert I just described, which is this model predictive control loop, and use it to train the deep learning policy. And then at test time, we just execute the deep learning policy. Okay? Turns out, if you do this for one run, it still makes mistakes, which we'll see in a second. If you do this for 3 iterations, so this is 3 loops of the dagger thing where you're executing the policy, and the model predictive control is saying, no, you should have done this, no, you should have done this, no, you should have done this instead. You get a learned policy, which is very similar to the model predictive control expert.
So the expert actually actively re-steer the
The
wheel?
expert is not controlling the vehicle. It's saying what you should have done, what the learned policy should have done. Okay? And the safety person is there to intervene
I see.
if the learner is going to crash the
I see,
vehicle.
I see.
Right? So then they, push an e-stop and the vehicle stops in some reasonable amount of time and doesn't blow up. Right? That's why there's these 3 parts of the system. Okay? So this is just showing what happens over iterations. Right? So if you just do a batch of this data from the model predictive control, sure enough, it goes off the course. If you do multiple iterations, it learns how to avoid crashing. Okay? And there's some T-SNE showing different feature maps. I don't know what to do with that. But there you go. Okay, that's the summary of kind of this version. I thought this was one of the coolest implementations of this idea, but there's been some more recently that are also super cool. Let's see. So Lee et al. Has everybody seen like the Boston Dynamics, various walking robots, et cetera? Okay, so those were originally developed at CME, actually, Mark Rabert's leg lab over in Wien long ago. And they are completely, this may not be true anymore, but up until very recently, these were completely engineered systems, right? And they have a combination of state machines. So they are in different phases. So the simplest version of these was kind of hopping robots. And there'd be like a flight phase where the robot would be in the air, and then a state when it hit the ground. And then in each of those states, there was a control loop, a manually engineered control loop of what the robot actuators should do in those loops. So these things are super complicated and super manually intensive to build, right? And that's why the leg lab was so impressive that they were able to build these things like the Atlas robot and the Big Dog robot, et cetera, all by engineering those policies. Those policies are blind to the world. So the only data they're taking in is, the more recent ones are not, but the classic ones are blind to the world. The only data they're taking in is effectively proprioceptive data. So data about where the body is in space, and then things like joint angles and joint velocities. Okay, so they're blind and they're walking blindly. Okay? And so the question asked was, could you build a learning-based approach to this rather than a giant engineering effort to craft these kind of walking controllers? Okay. And the answer is yes. Again, in this learning by cheating paradigm. Next. This is a complicated version. Okay, so simulator gets built that simulates the robot you're seeing in the picture on the right, in the world. The simulation environment can provide all kinds of interesting privileged information. So privileged information like contact forces, the terrain profile, what does the terrain look like? Remember, the robot in the real world is actually blind, right? So it doesn't have any information about the terrain at all. It's walking in a open loop in the sense that it doesn't have any vision, right? But not open loop in the sense that it does have proprioception. You can get the actual terrain profile. You can get friction coefficient. You can model disturbances. So I can tell you, there's a force pushing on you in some direction. You can then build an automatic set of terrain. So in fact, the way these were trained is that there's a curriculum of terrains that get increasingly more difficult. Now you can run a reinforcement learning algorithm to generate a policy that is providing torques at each joint. I believe that's the output control. It might be angles, and then there's a low-level controller that moves to those angles. And run RL. I don't remember which particular RL algorithm they used, but I think it was one of these kind of very brute forcey sampling around policy parameters. Make up some cost function of what's good. Their cost function is, well, it's bad to fall over. It's good to make progress. It's very simple cost function overall. And yeah, there is a low-level controller which is actually doing the what torque do you need to move a joint to a position. So that's common to the whole system. Okay, you can run RL. Sure enough, with all these privileged features, you can build a thing that walks in the simulator. Okay, and then you can again online imitate. They're getting proprioceptive measurements, meaning measurements of the body positions and joint angles, at a frequency of 0.02 seconds, 20 milliseconds. They build a buffer of just that information, feed it in to a time convolution network, and then output the action that would have been chosen by the policy that was learned in the simulation. That make sense? Train it on policy in the simulation. Okay, and I don't have a good video of it walking around, but I do have video of the next step up on this. Oh, did we lose it? Sorry about that. I'll skip the video on that, but sure enough, it can walk around. They show it walking around all kind of rough terrain in the Alps, which is pretty cool. But I want to show you a further enhancement to this, which is for some problems, it turns out you do actually have to look at the world around you and see what stuff is out there and respond to it, as opposed to just be purely reactive to what happens. And so this is work from Stanford and Chris Atkinson here at CMU on robot parkour learning. So I'll show you the results. You guys saw a little of this last time. And I'll show you how it works. You can see it ducking under that object, right? It's very hard to get something purely reactive to do this kind of stuff, as you might imagine. So it's using the same kind of proprioceptive information, but it's also using camera, and it might be a depth sensor. It might be a depth image as well in this particular work.
So the expert learns in a simulated environment.
Yep. I'm going to show you that in the next. Yep, it's almost the exact same paradigm, except you also provide as input to the learning algorithm a sequence of images. It's a pretty cool one. Okay, so there's a couple things that are additionally interesting about this. My memory of this one, so I'm going through a whole bunch of papers, so I'm trying to remember how each of them work. My memory of this one is they had a curriculum, again, of different object types to conquer, right? To climb over, go under, et cetera. And they actually trained basically a different policy for every element of the curriculum. So the teacher policy did not generalize. It worked for this terrain, and they built a whole bunch of different terrains, and they just built a little RL thing that could solve each of the terrains. Okay, the student then is the one that generalizes. So the student looks at just the camera images, it doesn't get the individual terrains, right? And it's told to follow the teacher in all of these terrains. And so the teacher is a different teacher every time. So there's like an expert for each terrain, and it's learning to mimic all of the experts. So I thought it was an interesting approach. Apparently that was much easier than trying to learn one policy that worked in the privileged thing in all the different terrains. It's kind of an interesting approach. Yeah.
Would it do well in kind of combinations of terrains? As in, if there was,
It does. It seems to do well if it transitions between them, right? Which is kind of interesting, right? Because as you say, or as you're, I think, hinting at, right? There's no, in the simulator, there's no like multiple terrains happening, right? But yes, it does seem to learn to transition between the different terrains. Recently, a whole bunch of papers have come out and applying this to manipulation as well, the same idea of manipulation. So again, the kind of expert gets a detailed point cloud, detailed description of the object. Here's the feature policy. It's a detailed mesh description of the object. It gets to do a ton of work offline to figure out all the places that it could grasp an object, figure out where the best one is, and then move the robot to go pick up the object, right? And then the policy is learned so that it does that based only on a camera image, right? So it does the same thing based on camera image, and again, proprioception of where the arm actually is. Show a more detailed version. Show a more detailed version of a tactile version of that in a moment. The phrase learning by cheating, due to Vlad and Colton in this paper. So this is kind of an interesting one. So this is learning to drive, right? So self-driving in cluttered environments, right, with other vehicles moving around, as opposed to the Byron Boots work I showed you earlier, where you're just learning to do high performance driving. It's all happening in a simulation. The privileged agent is using the ground truth position of all the actors in the world. And it's cheating in another way that I thought was really interesting. It knows the future positions of all the actors in the world. So it actually has the trajectories in the future for non-reactive actors, right? So it says, I know where they're going to be in the future. And then it learns, this privileged agent learns to plan in a world where it knows where everyone is going to end up in the future. Does that make sense? Turns out driving is much, much easier if you knew where everyone was going to be. Then, in fact, you can craft a pretty simple cost function, which is like, don't go off the road and don't break the law, right? Like, don't drive over the yellow line if you don't have to, and don't collide with anything. And like, that's pretty much it. You just kind of wait through those terms. You can build a thing. If you know where all the actors are all going to be in the future, you can build a thing that drives perfectly fine, right? So it's actually a very easy problem, relatively speaking, at that point. Okay, but the actor that you want to train is just going to take, again, a sequence of camera images, right? In this case, simulated camera images, the whole thing in this one is in simulation. Simulated camera images and map those to steering commands, okay? And it's doing it based on an expert that has privileged access to the environment, which is kind of interesting. So keep that one in mind, because that seems like really cheating in a way that's worrisome. Sanjaban Chowdhury was one of the ones, I'll talk about, I think, his key insight later as to what are these algorithms actually learning. Sanjaban did a whole bunch of work on this. This is work from Dieter Fox at NVIDIA. It's kind of an interesting version of this. So they want to do problems where you're like placing an object and you're doing it based on feel. So the feel it in your finger and then placing an object like pen in a hole. Okay. So an interesting one. So they have the sensor. I don't know a great deal about the sensor, but apparently there's basically a camera inside. There is some kind of elastic thing that you can feel that has pressure on it that actually responds to pressure. And then the camera can apparently see the deviations in the elastic thing. I'll show you examples of that in a moment. This is the kind of images that the camera captures. And what you're actually seeing is deformation in that elastomer. Right? So it's a way of building a tactile sensor with a camera, which is kind of a clever trick. Sort of a detail to. So they did this in simulation. They built a simulated version of this sensor. I think you can see the physics of the actual force field, and then you can see the RGB image that is captured by the virtual version of that sensor I just described. Okay, and then you might be getting the theme at this point. In simulation, they train a policy that can do things like place a peg in a hole by feeling where the peg is and then feeling the forces on the hole that is trying to place it in. Okay. Then they observe that their sim to real is really good, which is cool. They do a slightly different version. So they do the following. They have this privileged state information, the actual contact forces, et cetera. They build an expert policy and an expert critic, okay? Then for the high dimensional student that sees the observation in the real world, they use the expert critic. So they're basically doing the aggregate thing I described, right? They're using the expert critic to decide how good each control action would be, okay? And then they're cloning a student policy, actually taking advantage of not just the actions, but the cost of those actions, which is kind of interesting. They observed this worked much better to use the cost of the actions. Almost all the papers I talked about before did not use the cost of the actions. They just took the best action being taken by the policy. Okay, and be kind of dull if it didn't work, but.
This one actually uses aggravate.
It does. It's actually even more sophisticated than that. It uses aggravate, but then it learns a critic for the student, which is effectively pre-trained on the critic for the privileged teacher. So it basically starts with the critic of the teacher. That's its initialization. And then it learns an actual critic for the student. So you could think of that as it starts out as aggravate and turns into RL over time, right? It's eventually becoming a critic of the actual policy, the actual high dimensional policy. Right? So that's it's unclear how important that transition is. They did not do that ablation. So hard to tell whether just aggravate would have been enough or if starting it with aggravate and then moving to.
But aggravate would probably do better than just dagger.
That is what they said, yes, that it worked significantly better than just dagger. That part, I don't remember if it's in the paper, but Dieter mentioned that explicitly, that worked significantly better. Okay, so we have a recipe now. Okay, here's the recipe in a nutshell. Build a simulator. Everything we talked about had some kind of simulator involved. Even the car going around the track had a little simulation of what the car was going to do so that it could decide what trajectory in the model predictive control loop to choose, right? So it had some possibly very simple simulation. Learn or just plan. Maybe you just do model predictive control, or like Stefan did, you just build a tree search and look out some depth in a tree search to solve for a teacher policy using whatever information you can use to cheat that will get you a good policy. Okay, that's the kind of key step is what can you take advantage of that the simulator can provide, but the student is not going to know. Okay, a very common variant of this is no simulator perfectly matches the real world. A surprisingly impressive, a thing that has a surprisingly impressive results is you build a simulator, it's fairly imperfect, but then you sample different parameters for the simulator. So think about like the walking robots, right? You consider the robot has some actual mass, I don't know, maybe it weighs 5 kilograms. But you do a sample of the masses of the robot. So maybe you get some samples that are 5 kilograms, some that are 5.1, some that are 4.8. Then you sample things like friction coefficients. So there's some actual friction coefficient that maybe you measure, maybe there's some noise in that measurement, and you sample possible friction coefficients. And you try to build the teacher policy so that it works in all of those simulators. Okay? So you try to average over these sample simulators, right, where they differ in this kind of parametric way, and build a teacher that works in all of them.
A single teacher.
A single teacher that works in all of them. Yep. I've never seen the version where you build, the closest is the parkour robot, where you're building a different teacher for each one. I have never seen that done with, this technique is often called domain randomization. In the old days, it was called Bayesian robustness. So robust in an average case sense. You work well on average over simulators. As opposed to typically robustness means you work well in the, sorry, Stephen, in the worst case over simulators. Okay, so that's step two. Step three is you're going to train a student policy that uses the modality of input that the real world actually provides for you. I'm going to plug back in.
Sure.
Surprisingly non-robust.
Need the Bayesian.
Yeah. Need some domain randomization. Okay, then we train a policy. I'll just sit here tweaking the thing. Then we train a policy, student policy that uses the modality of input, say simulated camera images, and the teacher policy provides corrections of what the student policy should do. Optionally, use the teacher critic instead of just its actions. Then we use it in the real world. We apply this thing, sit it down in the real world. Optionally, we do RL fine tuning in the real world. Some of these papers then do an additional RL step in the real world to improve performance. Okay, that being the expensive part. Okay, all the approaches that we assumed before, all the things we talked about, behavioral cloning, et cetera, assume that the learner and the expert have the same information available to them. That is by design not true here. Okay, and it turns out there's a notion called a partially observed Markov decision process that we're gonna dance around a little today, where the agent doesn't get to see the state of the world. So it has the same flavor as a Markov decision process, except the agent doesn't get to see the state. The agent gets to see an observation, which you can think of as something which is a noisy indication of what state you're in, okay? It can vary from an unobservable Markov decision process where you get no observation at all to one which is the ones that are called decodable, in the sense that if you get a sequence of, like, say, 2 observations, you can figure out exactly what state you're in. Okay, so there's kind of a spectrum of difficulty of these partially observed Markov decision processes. Our robots are effectively in one of these partially observed Markov decision processes because they don't have the privileged information that the teacher policy does. Okay, you know, in this cartoon, the expert can see much further through the map than the robot can. Okay, turns out POMDPs in general are extremely difficult to solve. This is where, if I was a complexity theorist, I'd say things like NP to the PP. Good. We're going to spend our time today talking about a very simple version of a POMDP. Okay, it's often called a contextual MDP. Okay, so there's states, actions, rewards, transitions, just like before. There's an additional thing, which is a context, which is, you can think of as like a piece of the state that's hidden from the expert. It doesn't change over time. It's sampled initially at the beginning of the trial, and it doesn't change over time. So a nice example of a context would be, think about a set of mazes that you could be in, okay? So there's an agent walking around mazes. The context is what maze you're in. The state is your XY position in the world, okay? And no one tells you what the maze looks like around you, okay? So these are problems where you may have to even do some exploration to go figure out what to do. Okay? That's the notion of a contextual MDP. Okay. Context can affect both transitions and rewards typically. In our model of the world, the privileged expert sees the context, but the learner does not. This is a kind of a simple version of what's going on in these situations. Okay, so the first thing you might ask is, every one of these examples I gave you used something Dagger-like or RL-like or both, and you might ask, was that necessary, right? Because it'd be way cheaper, right, if you just collected a batch of data, like think about the robot driving around the track. It'd be so much cheaper if you just collected one batch of data of the model predictive control expert driving around the track a whole bunch of times, maybe from different initial states, build a batch of data, train the thing, right? It's very annoying to have to like go rerun this thing, right? Or run simulator in the loop with the learning algorithm, right? It's difficult, and you could very easily ask, is it necessary? Many of these things do not ablate that step. Nevertheless, the fact that they did this much harder thing suggests that it didn't work without it. Is the only thing I can say on those. When I know the authors, that's generally the claim, but I can't prove that for much of these papers. They seem to have done a much harder thing. Presumably it helped. But for some problems, right? So for some problems, you should actually just do this behavior cloning thing, collect a batch of data from the expert, train a policy that maps history. The reason why it's important to map history in almost all of these problems, there's a buffer of sensor data that's provided to the expert, right? It's not one camera image, it's like 4 camera images, right? It's for a lot of these things, from a sequence of camera images, you can get much closer to the privileged state than you can from just a single one. Get a much closer approximation of that. So what I want you to think about is the policies map from some history, some subset of the history to actions. Okay, and turns out for lots of problems, this actually works pretty well. This is a Sanjiman paper. I don't know if Gokul worked on this paper or not. I don't remember, but he's done these experiments himself. If you do this with like a variety of kind of benchmark problems in reinforcement learning, these are kind of simple robot control problems, actually works quite well. The reason there is a thing that will come up when we talk about it later is there's actually very little hidden state. If you look at the kind of camera image view of the world, it basically tells you everything the privileged information does. And behavioral cloning actually works just fine. Similarly, there was work, I think this is out of Stanford, that shows that behavioral cloning based on humans doing certain manipulation tasks worked basically as well as offline RL. Interesting. Okay, so Sanjiman has this nice example. And I have seen things very similar to this, so I think it's worth going through. He calls it the curious case of belligerent lane changing. Okay, so we're gonna set up a very simple learning problem for self-driving. We're gonna learn to change lanes. Okay, so the output space is should I change lane or not? Right. So basically, should I in this case move to the right or not? Okay, and there's gonna be a lot of features. So a feature is is there a disabled vehicle on the shoulder? Right, you often want a lane change away from a disabled vehicle on the shoulder. How far are you from the exit you intend to take on the highway? Okay, how congested is the traffic? Really important one, if I were to go in front of the actor, say behind me, how hard would they have to brake to not hit me? Right, that's a very reasonable thing to use as a feature. Okay, very natural to use past actions as well. Right, because lane change decisions are typically smooth. You typically don't like oscillate between making a lane change decision. You like make one and then commit. Okay, okay, so that's the learning problem. We get a bunch of data of human demonstrations of them doing this, humans lane changing. We trained a very simple classifier, it's a binary classification problem. Okay, its validation loss is low, we deploy. Great. Okay, very easy to build a thing that has 99% validation accuracy on this problem. And it does this very interesting thing at test time, which is it may make a decision, that 1% incorrect decision. It should then become very clear that it should not continue to make that decision, right? So maybe this example was on the boundary. Maybe it thought it could get ahead of that actor, would be okay, right? But by this time step, it should be very clear that it should not do that, right? However, bad things happen. Okay. Why didn't the lane change abort? This is not a real world. This actually happens if you try to train classifiers like this. No humans were injured in the training of classifiers like this, to be very clear. So what basically happens is the past action is extremely strongly indicates what you should do, right? So much so that the temptation of all the learning algorithms is just to cheat and just copy the past action. Because basically that gets you 99% right? And maybe they do a little bit more than that and they like make an initial decision as to whether to lane change or not, and then they just copy their actions from then on. Okay? Again, our usual problem of test and train distributions are not matching. Okay. This is such a common, problem in robotics and self-driving. These are all just self-driving papers that are observing variants of this. Like one of the versions is vehicle comes up to say a red traffic light and then never goes again. Just stops, never moves again, right? That version's called the inertia problem because the vehicle has inertia. It's observed in this paper. Poor predictions can cause a kind of feedback and cascading of errors. Another version of the braking. There are examples of this all over, this kind of latching effect. My personal favorite, I don't think we talked about this one when we talked about Dagger before, this is a really old paper on a CNN driving a little tiny robot, toy robot. And they found that, again, multiple camera images, they were stereo pair camera images, human drives robot around, tries to avoid obstacles and make progress. That's all this robot did. They added In this case, what they did is they added multiple time steps, multiple successive frames. As soon as they added multiple successive frames, what the robot would do is just turn in circles. Like it would like start turning and then it would decide, when you turn, you often turn for a while, and it would just continue to turn forever. Right? So this is a crazy situation in machine learning, right? You have to remove features or the performance is just catastrophically bad. Okay. Turns out, people talk about this exact same problem in natural language. In this paper, the DeepMind folks observed some LLM that once it said cheeseburger would just say cheeseburger from then on. Cheeseburger, 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 cheeseburger. Basically, for the reason observed here, mistakes made early in the sequence generation end up getting amplified. So if you make a mistake and you say something that a human didn't say in training data, you often get it saying crazy things, right? And a very common one turns out to be repeating itself. Okay. The curious case of neural text degeneration. Okay, so unsurprisingly, you already know what we should do in this case. We're gonna aggregate data together. All right, this is a version of one of these things that Sanjaban did, but the cool thing that Sanjaban proved, which we're gonna talk about in a moment, is a particular, what policy you would expect this procedure that I'm describing to converge to. Skip that. So, summary, in many cases, behavioral cloning does work fine. It should definitely be the first thing one tries. You should definitely try it first, right, because it's easier. Okay, sometimes it often creates this undesirable latching effect. Seems to really be a problem in this privileged information setting, which is interesting. On-policy algorithms consistently work well. I'm gonna give you a toy example to try to understand exactly why this happens, okay? This is an example from Gokul. I actually think the original problem was from that DeepMind paper I described. They were actually looking at language models. So here's the contextual MDP. The actions you can choose are you can choose basically to look under one of these three boxes or pull one of the three arms from these kind of bandit, what are those things called?
Arms.
Yeah, but what are they actually called? Slot machines.
Slot machine.
Yes, that's what I'm looking for. Okay. In this case, there's reward behind one of the machines. Okay, so there's one machine that actually has the reward. And in fact, this machine is great because if you pull the arm, you basically will get the reward every time. Pretty awesome. Okay, learner only sees binary feedback as to whether it got the reward or not. The expert demonstrator is going to know what the correct arm is in this problem. So what you'd like the learner to do is something like this, like try an arm, see that it didn't get reward, try another arm, see that it didn't get reward, try the third arm, see that it did get reward, and keep pulling that third arm, okay? And then I want you to think about a long time horizon, like, I don't know, 1,000 time steps, okay? Good. We're gonna add a little bit of complexity to this. We're gonna add some observation noise, which means sometimes, even though you pull the wrong arm, you'll get a reward. Okay, with some small probability, so think of this as 10% of the time, you'll get a reward from the wrong arm. Okay? In this case, it looks like maybe more than 10% of the time. Okay. We're gonna learn from the human expert who actually knows the context. Okay, and again, you see the kind of noise and the rewards. And then I'm gonna add what's called trembling hands in game theory. So the human doesn't always pull the correct arm. So with some small probability, they trip and pull the wrong slot machine arm, okay? So they make a mistake, okay? That's the model I want you to think about. Okay, so they're gonna pull the correct arm, then occasionally they're gonna pull the wrong arm, and then mostly they're gonna get the answer correct. Okay, and what we're interested in is bounding the difference between, the average difference between the expert and our student policy, our blind student policy. Okay. There are two assumptions that are important and are true in this toy problem I just gave you. The first assumption is with one we talked about before, this idea of recoverability. So you make one mistake, like you pull the arm, it doesn't prevent you from getting nearly all the reward that's available to you, which is very much true here, right? You pull one arm, well, out of your 1,000 time steps, you didn't get reward on one of the 1,000 time steps. Okay, but you can get all the rest of the reward if you pull the right arms from then on. Okay, so mistakes are not catastrophic in the falling off the cliff sense here. The other one is what we would call asymptotic realizability, meaning the learner can do as well as or nearly as well. You can think about this as some other epsilon. The learner can do nearly as well as the expert if it's able to gather enough information. Okay, so over time, it gets enough information that it's able to do nearly as well as the privileged expert. Okay, so think about those two assumptions. Okay. Good. We're going to now apply behavioral cloning to this. So we're literally going to learn a policy that has some finite buffer of which arms there were and what rewards were received from those arms over the last k time steps. Right? Think about it as maybe 10 time steps. Okay. And we're going to then watch the expert, who is again going to occasionally pull the wrong arm and occasionally going to get noisy feedback about whether or not the arm gives a reward. Okay, we're going to watch that expert do it, and we're going to train a policy. Okay, no shaky hand, trembling hand, no observation noise. Corrector is 0. This is what behavioral cloning does. This is an actual simulation of this problem. Okay, not good. It pulls the wrong arm and then just continues to pull the wrong arm forever. Okay, trial dagger, it tries arm 1, doesn't get reward. Tries arm 0, doesn't get reward, tries arm 2, eventually gets reward, keeps pulling that arm, same situation. Okay, so in that setting I just described, this is number of time steps that you can pull the arm. Okay, behavioral cloning basically gets effectively, I think there are 5 arms in this case. It basically is similar to choosing just a random action the whole time. Just basically effectively chooses it at random. You only get up to 0.8 because of the noise factor. Right. Good. Yeah. So behavioral cloning will sometimes work. So here's an example. So there's these 2 parameters, remember, the observation noise and the shakiness of the hand. Turns out with some parameters, if you get a shaky hand and no observation noise, behavioral cloning works fine. Okay. So it eventually figures out, hey, I can look 1 time step back, right? I can see if this gets me a reward. If it does, I'm going to keep doing that forever. Otherwise, I'm going to pick a different arm. Okay. And it will succeed in those settings. Small parameter changes lead to it not succeeding. Okay. Dagger gets the answer right. Corrector, eventually, after it makes a mistake, gets the answer right in those settings. It gets the answer right in this one. This is what I want to ask Google about, because I believe this is his slide. I think this emoji is just wrong. He's got the wrong emoji, because it's getting the answer completely correct on this problem. All right. Same thing. They're getting the right answer. What you see here is actually pretty interesting. This is a plot of those 2 parameters, the observation noise, the shaky hand, okay, going from 0 to 1, 0 to 1. And this is what happens if you do the behavioral cloning kind of thing, right? You get a phase transition, actually. So it basically, there is a place where you vary the observation noise and the shaky hand noise. There is a place where it works and you get almost perfect reward. And then a small parameter change and you get almost no reward at all. What's interesting is it is actually like a steep phase transition. You get from like getting it all right to getting none of it right at all. Right? And the reason is basically because the behavioral cloner transitions from just copying its past action, right, to actually looking at the history of observations and rewards. Right? I find it personally interesting that you don't see like a smooth change. You don't see it get it like 50% correct, right? You see it go from complete failure to complete success and nothing in between on these problems. The on-policy algorithms always work. The only place they don't work is where the observation noise is such that you actually can learn nothing about which arm has the reward. And so there's nothing to be done in that case. You'll always get that problem. Okay. If you try to actually bound the performance in these problems, guess what? Performance difference lemma, as always. Only two things you need to know, simulation lemma and performance difference lemma. Simulation lemma is coming. Okay, the performance difference will be bounded by the product of the following two things. Recoverability, which is if you make a mistake, what's the total additional cost you're going to pay for one mistake, okay? That times the average of this idea like in Dagger of like epsilon error at each time step, the average of that over the time horizon of the problem, okay? So how well can you do on the aggregate data set over time if you assume the problem is asymptotically realizable, meaning you gather enough information and then you can do as well as the privileged expert, then this thing's going to zero. Right? And so your performance gap is going to be small. So again, it doesn't have to actually go to zero, as long as with enough information, you can do nearly as well as the privileged expert, you're going to have the recoverability times how close to the expert you can do when you have enough information. Okay, this is not true for behavioral cloning. You get this term in here, which is a ratio of the data collected by the expert and the data collected by your policy, and this can be arbitrarily large. And that's the tightest bound you can get for the behavioral cloning case. Okay, so summary, on-policy algorithms make mistakes initially, generate feedback, asymptotic realizability ensures that they get good performance eventually. Off-policy algorithms, if they make mistakes initially, their history diverges from what the expert does, and then their performance blows up. Right? And again, it blows up in this discontinuous way, which is the thing that I find perhaps most interesting. See more examples of that. This is an example. I observed before that if you do these kind of simple control problems that are benchmark reinforcement learning problems, I'm trying to remember which one this is. This is a half cheetah, which is like you have to make this little two-dimensional robot walk, and you're trying to make it walk at some speed. Okay, that's the target goal. If you do these problems, and Ant is a bigger little robot, a more articulated robot that you have to make walk. If you provide the full state, behavioral cloning works absolutely fine. Okay? If you add some state that's hidden, so in this case, the latent state is the speed that the robot should run at. So you give it a speed that the robot is desired speed that it's supposed to run at. The expert knows that, and the learner only gets a "are you moving too fast or not" indicator. Okay? Then these things like behavioral cloning again fall apart. Right? So if you deny them some feature, they tend to perform very poorly. The on-policy things figure out how to recover. Okay, so here's a question for you all. Should training from the privileged expert lead to an optimal policy for the student? So I build this privileged expert, and let's say I get a privileged expert that's optimal. Okay. If I use it to train my student, am I getting the best policy the student could do, given the student's available information? Why or why not?
It might be the optimal, but it's not guaranteed to be, I think.
Yeah, in what kind of situations would you expect it to fail? To not be.
Or yeah, there might not be a deterministic function to recompute the same action at test time. So it's just basically, imagine if you take everything away.
Okay.
Then at test time it'll just do random actions, right? With a diffusion policy or something.
Yeah, so that's an interesting example that might be true. So imagine the student has no inputs at all, right? Then I'm sure we can concoct problems where you would be much better to randomly choose actions than you would be to constantly choose the same action. Right? I agree. That's almost certainly true. That's almost certainly true. Let me give you a hint. Will the student ever explore? Think about a maze problem for a moment, where the privileged expert knows the maze in advance, okay? And the learner doesn't. Will the learner ever try to explore? Why?
Are you arguing that the domain is too optimal? So it never sees mistakes, basically.
It never sees exploration or information gathering actions, right? Because the privileged expert always knows exactly what to do. Always knows exactly what to do, and the impoverished learner, right, only sees some view of the world. So the optimal thing for the impoverished learner to do might be go gather more information and then do something, right? But it's never going to get demonstrations of that, right? Because the privileged expert's always just going to do the right thing every time. So what will happen in those cases, like in this kind of maze case, is it will pick some policy and it will go try to execute that policy, and it will either succeed or fail, right? And then it might go try a new policy, but it will never, if there's a go turn the light switch on and you can see the whole maze, it will never execute the action go turn the light switch on, because the privileged policy always knows what the maze looks like. Okay, so that means there's a gap here, right? It means, in particular, there should be a gap between if we just ran RL on the student policy with no privileged expert. We just ran straight RL on that policy. There should, in general, be a gap between doing that and training the privileged policy and then cloning that to the impoverished policy, right? So then that begs the question, why would you ever do this thing that's clearly worse? Anybody? I actually don't know the answer to this, but I'm interested in, I have thoughts, but I'm interested in your thoughts. Why would I ever do this thing? Why wouldn't I just run, like for all these problems, why didn't I just run RL in the space of the student?
Does it not converge?
Generally seems to be true. It generally seems like it, for many of these problems, the harder the problem, it seems like it often doesn't ever find a good policy. Right? It seems like it can be just very, very hard to find a good policy on these problems, for instance, that have like camera image input. Yeah.
Probably like large action and observation space. So if you kind of explore through that just by using like reward signals, you might have to just be very sample inefficient.
Yeah, it seems like for some of these problems it can be super sample inefficient to do so, because you just have to do a huge amount of exploration, right, to figure out like how to map those camera images to robot control torques. But if you cheated and got all that information up front, it seems like it's much cheaper to do it that way. So, question, what does it approximate? So it's not going to give you, this two-step procedure is not going to give you the optimal policy. Is there something that it actually is going to give you? Can we characterize the solution that's going to come out? Okay. I never thought of this before, but Sanjaban Chowdhury did, and actually solved this problem. And there is a known answer to this problem of what you get out if you learn the privileged expert perfectly, clone it to a impoverished expert perfectly. If you do both of those steps perfectly, okay? And consider the case when the impoverished expert can have arbitrary history in its policy, so it can look back arbitrarily far. You have to have that caveat. Then it turns out what that two-step procedure will converge to is a very well-known approximation to POMDPs or stochastic planning problems in general, that in the POMDP community is called QMDP, in the planning community is called hindsight optimization. And I'm going to describe to you in words, and you can see the map, I'm going to describe to you in words what the hindsight approximation is. Okay? And it is shockingly effective on a particular set of problems. Not all problems. In fact, it's terrible in any problem you have to explore. But in problems where you don't have to explore, it works way better than you would think it would. Okay? Here is the approximation. Keep a distribution over the underlying states you might be in. Okay? So build what's called a filter that estimates, given the history of observations you've seen, what is the likely underlying real state that you're in. Okay? Keep that thing around, all right, and constantly update it as you get new observations. Update your belief, your probability distribution over underlying states. Then think about imagine there's only two actions you could choose again because it's simpler, left or right. Think about choosing left, and then think about after you chose left, all the uncertainty will be removed, okay? You're just going to end up in one of the states in proportion to your belief of being in that state, and then you do the optimal thing, okay? Does that make sense? So the thing you're imagining in QMDP, I'm uncertain about where I am in this room, okay? I could step left, I could step right, but after that time step, all will be revealed to me. I'm gonna know everything after I make that action choice, okay? Should I choose left or right? That is the QMDP approximation. Okay? It imagines a world in which you're uncertain now, but in the immediate future, you're going to not become uncertain. What should you do to hedge against that uncertainty you have?
You calculate the Q values for the next state.
Right, because for the next state, all the uncertainty's gone, and so now you're back in a regular MDP, right? So by assumption, if you can solve the MDP, which is usually true, right? For many of these problems, it's really easy to find the policy for the MDP and really, really hard to find it if you only see observations, okay? So you do exactly that. You solve the underlying MDP, and then you average over your uncertainty about what actual state you're in, okay? And then you think about what the value is of the underlying MDP, okay? That's the QMDP approximation. So that is actually what these two-stage procedures converge to. They don't converge to the optimal policy overall, they converge to the QMDP approximation of the optimal policy, which I think is a kind of an interesting characterization. So you can tell what the optimal behavior is going to be. Okay, good. And that is my summary of learning by cheating.
You have 5 minutes, but
I can make stuff up, I can answer questions.
questions?
The QMDP thing is kind of subtle, but it seems like this should never work. It also reveals why it never explores, right? It never explores, the QMDP thing will never explore because it always believes at the next time step, I'm gonna know everything anyway. So there's no point in like gathering any information now, right?
So the statement is, if you do the 2-step perfectly,
Yep.
you obtain an impoverished policy that achieve the same Q value.
She's the same performance, in fact, is the exact same policy as what would be executed if you were to solve the POM-DP with the QMDP approximation.
But the impoverished expert will be, every time step will be in a dark state. It would just go through the same exercise of.
Yes, it goes through the same exercise of, I'm not sure where I am, but I'll definitely know where I am at the next time step, right? That's what the QMDP policy executes. It says, I don't know where I am now, right? I've got some idea where I am, but whew, I'm definitely gonna know at the next time step. So I'll just pick the action, which is gonna get me the best reward on average over my uncertainty now, if I were to act optimally with all information 1 step in the future. And then it does that again. And it says, oh, dang.
In reality, you never know the true state.
Right, and it takes a step and it goes, oh dang, I didn't actually learn where I am. I'm still somewhat uncertain about where I am. Well, I'll definitely know at the next time step, right? So I will just average over my uncertainty of where I am now and think about what the optimal thing would be to do once I, at the next time step, know where I actually am. But I never actually find out where I am.
But the distribution of states never change. Every time step you go through the same.
The distribution of states does change because you gather an observation. So you gather a new observation, and now you have a new belief about where you are in the world, right?
Got it. Cool.
That is the summary of QMDP, and I think it's interesting that you can so cleanly characterize what this 2-step procedure converges to, and that this other thing is a like super widely used approximation in planning.
Yeah.
So for the, I guess, either the Leggett case or the other general case where you say using behavior cloning to learn from a teacher, is that process still using reinforcement learning or is it using the supervised learning where you're kind of giving like a.
Could you ask the question again? I was having a hard time with it.
Yeah, no
So
worries.
in this problem?
Yeah, where you have like a privileged state,
Yep.
teacher policy, and
Yep.
trying to have a student policy learn
Yep.
from a different set of observations.
Yep.
That's like kind of hidden. Do you use the same method from before, like just tell it the actions,
Yes.
mapping observation to actions, like
Yep.
a supervised?
But it's trained in this on policy way, right? So you collect data set of the privileged thing moving in the simulator and what it should do, right? And then the training data looks like, so you do that first, and the training data looks like say the camera image, let's say it's the camera view of this, the camera image and maybe the joint angles, right? That's the input. And the output is, what did the privileged expert do in that situation, right? So the privileged expert sees like the full underlying state of the world, right? And that's your first training set, okay? Then you execute that. It unfortunately makes some mistakes, right? So now you execute the policy that goes camera image to joint angles to perform. And then you consult the privileged policy at every camera image and say, what should the student do, right? And then you take that data and put it together with the last data set you collected. And then you train a new policy, which is camera image to joint angle, right? You execute that one. And again, you consult the privileged expert and say, what should you have done in each state, right? And you take that data and you put it all together again. And you do that for enough iterations that hopefully it gets better and better over time.
Got it, okay. So there's no notion for the student teacher to have like notion of like what the reward of.
Right, most of them just use the action. Some of them weight the actions by how much reward the privileged expert would get. Like how much it prefers choosing action A over action B. Right? Some of them do that weighting, and that version with the weighting is called aggravate instead of dagger.
So I guess like, do people consider like maybe training using like a teacher, and then after that, you take that policy and run like traditional RL?
Yep. And some of them even do the, yes, that is very common, is at the end you run a little RL to see if you can further improve the performance, right? Because for instance, you could then learn to explore, right? If you run straight RL, it could in fact learn to explore and choose actions to gather more information. It seems mostly people don't do that, interestingly, or if they do it in the real world outside of the simulator. So we did this whole thing in a simulation, but now we have a policy that runs in the real world. Sometimes they will do a little RL at the end in the real world. It seems not that common that they do a little RL back in the simulator, but I don't know why. There's no reason that I can think of not to. Seems like it would just be strictly better.